Welcome back. This is the continuation of concept 11.1, section 11.1. So it is made up of multiple videos here, part A, part B, part C, and this is part D of the video. Um, there are so many techniques that you use in this section, which will be used in the even when you do testing the series of convergence in the later section. So understanding this section is important to follow through the rest of the sections in this chapter. For what values of R is the sequence R to the n convergent? The sequence R to the n is convergent when R lies between -1 and +1 inclusive. So in the interval -1 to 1, -1 open, 1 closed. And divergent for other values of R, and divergent for all other values of R. So the sequence R to the n is convergent for R lying between -1 and 1 and divergent for all other values. So limit is n approaching infinity R to the n equal to 0 when R lies between -1 and 1, and it is equal to 1 at R equal to 1. It's either case it is convergent. Whenever R lies to the right of 1 or lower than -1, the sequence would be divergent. You can look at the picture here. So you can give a value, say R equal to a value, choose a value between -1 and +1, let's say 1/2. And then then you find out 1/2 to the power n, n equal to 1, n equal to 2, n equal to 3, and so on. So when you notice here, when R lies between 0 and 1, you notice this red ones. If you see, the pink ones are all approaching the value 0. Then when R equal to 1, it's stationary, it's equal to 1. So it is either case it is convergent. When R is more than 1, when R is more than 1, you see that the sequence is kind of divergent. And similarly here, when it is -1 to 0, then it actually, though it alternates, but it is approaching the value 0. But when R is lower than -1, then it is kind of divergent. The values are divergent. So this is something to note. So R to the n is convergent. Sequence R to the n is convergent when R lies between -1 to 1, inclusive of 1. In all other values, it is divergent. When is the sequence increasing or decreasing? Even this concept will be used quite often later in series 2. A sequence The sequence AN is called increasing. Is said to be increasing if A sub n, or the nth term, is smaller than A n plus first term, the next term. For every n more than or equal to n. For all n more than or equal to 1. What it means is A2 should be smaller than A3. A3 should be smaller than A4, which is kind of making sense. So if you just plot these ones here, then you will have A1, then A2, A3, A4 like that. That means the function is, the sequence is increasing. So A1 less than A2 less than A3 less than A4 and so on. The sequence AN is called decreasing if AN is more than AN plus 1 for all n more than or equal to 1. So it is decreasing That means it should be A1 and then A2 and then A3 like this. So it should be decreasing like that. So if you notice here, A sub n, let's say A3 is more than A4. So it will be A4. A3 is more than A4. A2 is more than A3, like that. A sequence AN is monotonic if it is either increasing or decreasing throughout. It should not be increasing for certain terms and then decreasing for certain terms. It should be continuously increasing or continuously decreasing. Then it is said to be monotonic. A sequence AN is bounded above if there is a number m such that AN less than or equal to m for all n more than or equal to 1. It's bounded. That means AN is less than or equal to some quantity for all n more than or equal to 1. It's bounded below if there is a number m such that m is smaller than or equal to AN for all n more than or equal to 1. If it is bounded above and below, then it is said to be a bounded sequence. In order for a sequence to be a bounded sequence, it should be both bounded below and bounded above. Every bounded monotonic sequence is convergent. That's known as monotonic sequence theorem. So now let's see two examples where we prove increasing, decreasing. We are testing whether the sequence is increasing or decreasing. Is the sequence 3 over n plus 5 increasing or decreasing? That means if you recap the ideas that we mentioned, so it is increasing if an is less than an plus 1, decreasing if an is more than an plus 1. So even this idea will be repeated quite often later in series. So let's find out. This is what we have inside the curly bracket is the nth term, right? Without the curly bracket, this is the nth term of the sequence. Then what is a sub n plus 1? So change the n to n plus 1. So it's n plus 1 plus 5, which is 3 over n plus 6, right? So we know that n plus 5, the denominator of an, is smaller than the denominator of an plus 1, because n plus 5 is smaller than n plus 6. So if I take the reciprocal both sides. So 1 over n plus 5 is more than 1 over n plus 6. The inequality, if you flip, the inequality will get reversed. If you take the reciprocal, the inequality will get reversed. So now we multiply both sides by 3 because that is what we have in the nth term. In the nth term, we have 3 on the numerator. So we have 3 on the numerator. So multiply both by 3. Then what we notice is the left-hand side is an, the right-hand side is an plus 1. So we have an more than an plus 1 for every n. More than or equal to 1. So which of the two conditions we are proving? The an is more than an plus 1 for all n more than or equal to 1 is a condition that we have proved, which means the sequence n 3 over n plus 5 is decreasing. That is your conclusion. So whenever you are asked to, if you are asked to prove or test whether the sequence is convergent, decreasing or increasing, you have to prove a generic way, the way I have shown in this example. You cannot just list the sequence members. Oh, I'm able to see that the sequence members are decreasing. Though it is trivial, but you are expected to prove that in a generic way, the way I have shown in this example. Show that the sequence, next example, show that the sequence A sub n, which is equal to n over n square plus 1, is decreasing. So as we did in the previous problem, where the previous problem has a constant on the numerator. So it is easy to compare the denominators of an and an plus 1, and then we can just multiply by the constant. We cannot, the inequality is not going to be altered. But here being n, the numerator being n, that makes a whole difference. You cannot multiply one quantity by n, the other quantity by n plus 1 and make a comparison. So in this case, whenever the numerator, whenever you make a note of this, whenever you have the numerator, if numerator is not a constant, then compare the sequence to a relating function. Compare the sequence to a relating function, like one of the problems that we did earlier. So consider the function f of x, which is equal to x divided by x squared plus 1. So we are changing, change the n to x. So we know that we have to show that this function is a decreasing function. So if this is a decreasing function, then the given sequence would be a decreasing sequence. So how do you show that a function is decreasing? We have to show the derivative is less than 0 eventually, meaning that for all x more than 1, or eventually. So even if it is not from 1, but if it eventually decreases, it's okay to say still the sequence is decreasing. So we are going to consider the derivative test. So apply the first derivative test, or increasing, decreasing test that you did in chapter 4. So let's find out the derivative. F prime x, so you have to apply the quotient rule. So denominator times derivative of the numerator minus numerator times derivative of the denominator divided by denominator square. So what you're applying here is the quotient rule. So it is x square plus 1 minus 2x square divided by x square plus 1 the whole square. So if you simplify, it is 1 minus x square divided by x square plus 1 the whole square. This is f prime x. So whenever x square is more than 1, so we have to say that f prime x is less than 0 eventually, right? So in this case, f prime x is 1 minus x square. The denominator x square plus 1 the whole square is always positive, being a square. X square plus 1 the whole square is positive always. So f prime x is less than 0 whenever x square is more than 1, right? So 1 minus x square. So whenever x square is more than 1, the numerator would be negative. Numerator is negative, denominator positive. So f prime x would be negative eventually. So whenever x is more than 1, or in other words, f is decreasing on the interval 1 through infinity. 1 through infinity. So if f is decreasing, this tells us that the sequence, so the relating sequence is decreasing, the relating series, relating function is decreasing. F is a function, relating function is decreasing. That means the sequence, the given sequence, which is n divided by n squared plus 1, the sequence is decreasing. So oftentimes we use this technique um, when we are testing series later on, how to find if the numerator of the sequence is not a constant, then if it is n or n square or something related to n, which is not a number, then you would do this technique. You will consider the relating function and show that the relating function is decreasing by taking its derivative and proving it's less than zero eventually, then that will tell us the sequence, given sequence is a decreasing one. Then there are some problems done in this section video. Please refer to those. Problem number 29 and 73. Problem number 29 and then also 73. These two are done in the section video. Please refer to the section videos for 11.1. So I did many examples in this section. The reason being, some of these examples will become very handy, will be handy to do testing of the series later on in this chapter. So some of the techniques, especially the one that we proved here, showing that a sequence is decreasing, this condition will be, this idea will be used quite often. And also the idea, this one. So looking at the relating function and deciding the limit of the sequence can be determined uh, by finding the limit of the relating function. This idea, example number 6. So some of these ideas will be repeated later. So it is better to understand this section more for the upcoming sections in this chapter. Hope these videos help.